Hello.
Hello.
Hello guys. Now we are in Faculty of Engineering, University of Indonesia. So we are from group 2.
Okay, in this video we are going to talk about derivative with three variables.
Come on, watching our video. Hello lovers, my name is Faisal Firdaus Samarullah, and in here I want to tell you about the definition and the concept of three variable. Thank you. Okay, now we're gonna tell you about derivative of function with more two variable. Okay, for a function f, x, y, z, there are three partial derivatives. The first is fx, x, y, z, fy, fy, x, y, z, and fx, x, y, z. So I'm gonna give you the example first. Yeah, f, x, y, z is cube, y square, and x 4 plus 2x y plus z. How the derivative? So if we want to search fx, x, y, z, we derivative this 3x square, y square, and z 4 plus, because we gonna search x, so we eliminate the x to y. Alright. Second, if we want to search fy, x, y, z, we derivative y to be 2x cube and y kill x 4 plus, we eliminate the x to be do y to x, and if we want to search fz, x, y, and z, we derivative z to 4x 3 y square and x 3. Here we minus this, and because there is z in here, just can his, and derivative from z is 1. So we know the derivative for fx and for fy and for fz. Okay, there is the example. If you want to know more, you can ask me. Okay, thank you.
Hello, my name is Rifana Ramadanti and I will explain about partial derivative. In mathematics, partial derivative of a function of several variables is its derivative to one of these variables, the other held constant. The partial derivative of a function f, x, y with respect to the variable x is variously denoted by the notation such as in f function of x, x, w, etc. Suppose we have a function of three variables such as w equal to function of x, y, and z. We can calculate partial derivatives of w with respect to any of the independent variables. For example, let function of x, y, and z be a function of three variables. Then the partial derivative of f with respect to x, written as del f divided by del x, or function of x, is defined to be like this. Now we are going to the example. For example, we have function f, x, y, and z equal to this, and all we want to do is evaluate the first partial derivative with respect to y at the point 1, 3, 5. First, we have to find fy. The derivative of y squared is 2y, and the second term doesn't have any y variable, so the whole thing is a constant that becomes 0. And the third term, we can find the derivative of 5y, which is 5. After that, we can substitute the point 1, 3, 5 to fy. After we calculate this equation, we have find the fy is 3149. That's the result.
Hello, my name is Adeline. I will explain about limit and continuity. The limit of a function of two variables has the usual intuitive meaning. The values of function x and y get closer and closer to the number L as x and y approach a, b. This is equal to this. Next, we might expect that limits for many functions can be obtained by substitution. This was true for many, but certainly not all, functions of one variable. Before we state a theorem that justifies evaluating limits by substitution, we give a few definitions. A polynomial in the variables x and y, where p and q are polynomials in x and y, assuming q is not identically 0. The following theorem is analogous to if function x and y is a polynomial, then limit x and y to a b function x and y result function a and b, and if function x and y result p x and y divide q x and y where p and q are polynomial, then limit x and y to a and b function x and y result p a and b divide q a and b. Next, continuity at a point. To say that function x and y is continuous at the point a and b require the following. 1. Function has a value at a and b. 2. Function has a limit at a and b. Third, the value of function at a and b is equal to the limit this.
Hello, my name is Fitria, and now I will explain about directed derivatives and gradients.
I want to tell you about directional derivative. This is the regular form from partial derivative. With the replacement of I or G using arbitrary unit vector of u, we can define that directional derivative of z is f in x and y on p in x and y equal to this. And the next is the relationship to gradients. If f has a derivative or locally linear in p, then f has a directional derivative in p in the random vector direction of u, and this regular form is equal to the gradients. And then the maximum rate of change. Example, if theta is the angle between u and v, then this regular form will be maximum value if theta is 0 and will be minimum if theta is p. This is the regular form from maximum rate of change. And the last is high and gradient curves. On the high curve, the value of f is constant. So if we move in the direction of the tangent vector u on the curve, the rate of change in the height will be equal to 0. This is the regular form. So the gradient vector f at p is perpendicular to the height curve f through p. And now I want to explain about partial derivative of f in x and y in 1 and 2, this, and the directional derivative of f in 1 and 2 in the direction of vector u in 0.6 and 0.8 is this. And this is the result.
Hi, my name is Vina Fadia Rahman, and now I'm going to talk about chain rule.
Recall that the chain rule in single variable calculus can be written like this, where first we differentiate the functions, then we multiply it with the derivative of function inside, which is g function. The same method can be applied in multivariable derivative, in this case, three variables derivative. We just have to differentiate the function with respect to variable 1, and then variable 2, and then variable 3, and then we accumulate these three derivatives. In Purcell's calculus, there are two versions of the chain rule. The first version, as you can see here, the x, y, and z can be differentiable at t. So the derivative will be like this. This is what I mean by differentiate the functions with respect to variable 1, variable 2, and variable 3. Let's jump to the example. So I have find the derivative and evaluate it at p per 3. So we can use the equation I've shown before, and so here is the derivative with respect to x, and it is the derivative of x. Then we got equation, and then we evaluate it at p per 3. The second version is this. So we can differentiate with respect to s and with respect to t, right? Basically, it's just the same version. Let's go to the example. So here I have find the derivative. So I have to use this equation. Then we just do it like before, like this, and then like this. We get this, and then we get this equation. Oh, this is the final answer.
My name is Jefferson and I'm going to talk about a tangent plane.
We've learned in high school about tangent lines. It's in 2D, 2 dimension. Now, we're gonna talk about tangent planes. They are in 3-dimensional graphics. Now, the basic idea is looking for a function whose graph is the plane that is tangent to a given point. Now, we have to observe the properties of the graph past the point x, y, and z point. Now, at this point, we can see that the point at the plane is intersecting or tangent to a graph that are 3-dimensional. Now, if you evaluate L, X, and Y, it's gonna be equal to Z. When a plane is intersecting a constant X, Y, Z value, the slope will be the same. Now, to solve this, we use a partial derivative with respect to X and Y constant. We can see that function fxy over X is gonna be equal to A, fxy derivative with respect to y is gonna be b. Now we can plot the function. It's gonna be lx and y, ax plus by plus c. Now to evaluate the point, we have to evaluate the point at the point x and x0. Now we can rewrite this equation into this new one. Now onto the examples. We are given that f, x, and y is 3 minus 1/3 of x to the power of 2 and minus y squared. Now the x0, y0, and z0 is 1 minus 2, and the z0, as we have known from the earlier explanation, is f1 and 1 minus 2. Now we plot this point to this function. We got negative 4/3. Now we plug in this negative 4/3 to the constanta. Now we move on to the partial derivative. We know that the partial derivative over x is a and with respect to y is b. Now we know that a is equal to negative 1/3 x to the power of 2, which is known from this equation. We got that. So the derivative of negative 1/3 x squared is negative 2/3 times x. Now we plug in x equal to 1. We got negative 2/3. Move on to the b. B, as we can see from the equation as well, is negative y squared. When you derive negative y squared, it's equal to negative 2y. We plug in the y equals negative 2. The results will be 4. Now we plug in all the answers that we got into the original formula, and we got negative 2/3 times x negative 1 plus 4 y plus 2, 4 times y plus 2, negative 4/3.
Hello, my name is Adildafa Yogi, and now I'm going to explain about maximum and minimum value.
To find maximum and minimum, we should use this equation and the partial derivative methods. This is the second partial derivative of function x and y with respect to x, and this is the second partial derivative with respect to y, and this is the partial derivative with respect to x and then with respect to y. And here's we have some condition. First, if the d is more than 0 and the second partial derivative with respect to x is less than 0, then the function is a local maximum value. And the second, if the d is more than 0 and the second partial derivative is less than 0, then the function is a local minimum value. Third, if d is less than 0, then the function is a saddle point. Last, if d is equal to 0, then the test is inconclusive. So here's the example. Find the extreme point of this equation. First, let z be the function of x and y, and then we should find the first and the second partial derivative of the function with respect to x and with respect to y. Then we get this, and we find this too, and we get 0. And to find the extreme point, we should use the first derivative is equal to 0. Then we get the extreme point, and do the same with respect to y. Then we get these 3 extreme point. If we're looking for the maximum or minimum, we should plug the information to this equation and we can make this table.
My name is Ilham Aksal. Now I'm going to explain about Lagrange multipliers.
Lagrange multiplier. When you want to maximize or minimize a multivariable function, subject to the constraint that another multivariable function equal a constant. Follow this step. Step 1. Introduce a new variable and define a new function as follows. This function is called Lagrangian, and the new variable is referred to as Lagrange multiplier. Step 2. Set the gradient of Lagrangian equal to the zero factor. In other words, find the critical point of Lagrangian. Consider its solution, which will look something like this. Plug each one into F, or rather, first remove the Lagrangian component, then plug it into F. Okay. This example 1, budget constraints. This the problem, and the question is, if your budget is $20,000, what is the maximum possible of review? Okay, this solution that $20 per hour labor cost and 170 per ton steel cost tell us that the total cost of production in terms of H and S is plus 170s. Okay. You can see in the screen. Next, we handle the partial derivative with respect to S. You can look in the screen again. Putting it together, the system of equation we need to solve is like this, and the H, the S, Lagrangian, you can see, and the answer is $51.77. Okay.
Thanks for watching. Don't forget to
Like, comment, and subscribe.
Yeah.